Hi, I'm going to go through the first of two videos describing the hashing or hash table project in our class. In this one, I'm going to go through the two main classes or main objects that exist in the program. That's a hash table and a list of buckets into which items can be placed, and kind of explain a little bit about the hashing function and how it picks which bucket your values are going to land in. In the second video, I'll actually just walk through the code and show you where this is taking place and show you where you need to add your code to make it work. So let me share my screen, and find the correct window here. We should be good. Here we go. Okay, what you can see on the screen is kind of a crude diagram that shows two basic classes. Now, this program, the project program I give you to work on, is a reasonably complete program in the sense that it will read in the JSON file, it will run, it will spit out some test output, but it doesn't actually do any hashing. The hashing relies on you writing two functions, at least two functions, a hashing function that converts the string key, which is the bus stop number, into a key that can be used as a number, as an index into the bucket list, and also a function to search the hash table for a given key, which is kind of the reverse of inserting it. And the two are very similar. So there's two classes. There's a hash table, which is basically a container that has, and you can see the value, the members across there. It has the number of buckets, which I've chosen in this case to be 5003. In the template code you downloaded, you'll see I've got it set to 10, which is an absurd value just for testing because obviously it's too small. There are over 4,000 stops in the JSON file. So I picked the next closest prime number. I went to Wikipedia and looked at a list of prime numbers. I said, if I make the number of buckets that are available to use for this hashing 5003, that'll hold for sure all 4,000 some odd stops. And it won't guarantee there's no collisions, but they'll all fit. Prime numbers are a little bit advantageous because having no factors other than one in themselves, they don't have quite as many collisions when you hash as would some other size, some other modulus in this case, that allowed for a lot of numbers to map to other factors. And of course, there's a bucket list. And the bucket list is the actual Python list or array, as we talked about, of buckets. And bucket is its own class, and it has just a couple of attributes. It has a key string and a value. And you could put more stuff in there if you wanted to put any kind of object. But for this program, all you need is to basically define a key, which is a string valued key you started with before you hashed, and a value, which is a description of the bus stop. So 3703, I think, is like Maitland Center or something. And you can see it here. If you look at the bucket list, bucket number 0 is currently empty. So if something happens to hash to 0, it's going to be really straightforward. It's going to be easy. You're going to put it in that bucket and you're done. Bucket for stop number 3072, I just picked one at random, which is some Maitland Center stop. I actually show you the hashing calculation that you need to do. And what these numbers are, 51, 48, 55, 50, those are the values for the ASCII characters 3072. So a 3 in ASCII, the character 3, is actually the number 51. I looked this up in an ASCII table, don't know these off the top of my head. 0 is actually 48. Numeral 7 is a 55, and numeral 2 is a 50. So I have code, and you'll produce code to go through character by character, a loop for, in this case, the length of the key, which is 4, and add up each individual character. So you'll get a sum there of 204. And when you mod that by 503, since that's a small number, it'll still be 204. So string key 3072 is supposed to land in bucket 204 in your hash table. And the same way with key 9833, which I think is Keller Road. Add up the values of 9 and 8 and 3 and 3 in ASCII, mod it by 5003, you get 215. Of course, there's a lot of buckets in between I don't show in this diagram. Suppose that you now pick another stop and it happened. That's fine. Let's talk about collisions. So you pick another stop, or there's another stop in your JSON file that your program tries to hash, and it does. And it turns out it has completely different. It's not 3072, but it hashes to bucket number 204. So now we have the makings of a collision. So you code an insert function that uses some method to resolve this collision. Now, the methods available, there are many, but the ones that you could are described in the Zybook, there's a linear probing, there's quadratic probing, and there's basically a collision list. And any one of those will work. I'll describe linear programming in this case, linear probing in this case. So you just, when you go to bucket 204, you see, oops, there's already something there. It's not empty. So there's not, I can't just put it in bucket 204 and be done. I need to find an empty bucket nearby without scanning too many buckets that can hold the new value that I'm putting in. That's where linear probing comes in. So starting from bucket number 204, I could go to bucket 205, 204 plus 1, see if that's empty. Maybe it is. If it is, I'm done. Otherwise, go to bucket 206, check there, and so forth. Eventually, I find an empty bucket, and I'll put it in the empty bucket. It won't take too long to find an empty bucket, so it's not really expensive of time. Notice what I put in the bucket, though. In addition to the bucket number 204, where I'm going to find it in the future, I also save away the original key 3072. I'm going to need that for the search function. And of course, the value Matewan Center is what I'm going to want to get back when I search for stop 3072. So linear probing is nothing more than going into an array, calculating a bucket number using a hash function, going into the bucket list, checking whether that bucket number is empty. And if it's not empty, searching linearly, in other words, 1, 2, 3, 4, searching down the list of buckets until you find the bucket that is empty and placing the value there. Notice that since it's modular, if you were very near the end of the list, it would actually wrap around and start back from the top. So we know the value. We know somewhere if our hash table size is 5003, we only have 4,000 something stops. Somewhere there's an empty bucket. Linear probing will find it. Quadratic probing is the same thing, but with a fancier calculation instead of a simple next bucket, next bucket, next bucket. There's a little more multiplying and adding that takes you farther up away in the table. So that we'll come back to that. So, okay, so now we've got a value inserted. We dealt with a collision that may have occurred when the value got inserted. The next thing to do is to think about searching. Okay, now it's time to find that value in another part of the program. We want to search for stop 3072 and see what its description is, Matewan Center. But we don't know that. So we hash the key again, 3072. We get the value 204. We go to bucket 204, but maybe what's in bucket 204 is not the key we want. Maybe something else previously hashed that bucket. It was a bucket involved in a previous collision. We again apply linear programming. We look at the stored key, and that's where this comes in. To know whether this is the right 204 or not, you compare the key you're looking for, 3072 in ASCII, with the saved key in the bucket, 3072. And if it is, this is the right bucket. If it's some other key value, then we start linearly probing, going 205, 206, 207, until we find a bucket whose key matches the key we're searching for. So that's how we resolve collisions on search. So linear programming is required both in insertion and in searching for a value. So in the Python program, there's a couple of classes. There's a hash table class, and there's a bucket class, which represents each of these buckets. And the hash table has a bucket list, which is essentially just an array or a list of possible buckets, 5,003 of them, as a matter of fact. So hopefully this will help you understand a bit about the hashing function. This is described in the Zybook, and they show this briefly, as always, in examples in some pseudocode. They have a pseudocode example for linear probing that you can use to create your linear, and they have a pseudocode example of hashing, both of which you can use to create the code you need to insert into the Python program. The trick with the Zybook is that their solutions, they don't actually give you the Python code for it. They give you some sort of pseudocode that looks to me like a mixture of C++ and I don't know what. But the basic steps are all there. If you see a while loop in that pseudocode, you're going to have a while loop in your Python. If you see an if in the pseudocode, you're going to have an if in the Python. So you can use those functions like 4.4, I think. There's a reference in the project description and in the code that tells you what section of the Zybook talks about this stuff. So there's a section on linear probing. There's a section on quadratic probing, and there's a section on collision lists. So those should be enough, should help you a lot in filling in the template Python program that I've supplied. Hopefully this addresses some questions. Obviously, you can let me know what questions you have, that confusions that this did not clear up, and I will be happy to respond to those. I will see you in the next video.